Let's dive into an in-depth exploration of the relational data model, a cornerstone of SQL databases that has been a staple in the industry for decades. This model not only defines how data is structured, wow, it's really crucial, but also plays a vital role in how we interact with that data using SQL. Just think of it as the blueprint for how everything fits together, allowing us to efficiently store and retrieve information. It's like having a well-organized library where every book has its place, making it easy for us to find what we're looking for. So, in this tutorial, let's break this down further and see just how powerful the relational model is in managing our data interactions. So far, we learned that a database is a structured collection of data that facilitates storage, retrieval, and management, making data organization easier. We explored the concept of data models and focused on relational databases, particularly using SQL to create and manipulate tables like books and categories. We discussed the importance of querying data, using join statements to enhance our results, and maintaining data integrity with various constraints. Finally, we highlighted the power of data analysis in PostgreSQL, emphasizing how these skills can aid in deriving meaningful insights from data. Now, we will delve deeper into the relational data model, understanding how it operates and why it's crucial for effective data management. We'll uncover its components and see how they interconnect, allowing us to manage our data intelligently. Ready? Let's get started. Now let's implement a command to create our employees table, shall we? The SQL statement we're using will establish an employees table with several crucial attributes. First, we're going to define the employee ID column, which is of type serial and designated as the primary key. This step is really important because it ensures that each employee record gets a unique identifier automatically generated by the database. That's essential for maintaining our data integrity. Next up, we'll focus on the name column, where we specify varchar 100 as the data type. This allows us to store variable-length character strings, so we can keep employee names up to 100 characters long. Following that, we define the department column using varchar 50, giving us ample space for department names. Now, as for the salary column, we'll define it as decimal 10-2 to accurately represent monetary values, including 2 decimal places for cents. By structuring our table this way, we create a clear and concise schema that makes data management and retrieval easy. Now, with this foundation in place, we can smoothly move on to inserting, querying, and manipulating employee data effectively. Now, let's dive into implementing the code to create the departments table and establish a relationship with the employees table using a foreign key. First up, we're creating the departments table, and within it, we defined a department ID as a serial primary key. This is super handy because it allows the database to automatically generate a unique identifier for each department, ensuring that each record is accessible individually and, crucially, without duplication. Next, we're going to modify the employees table by adding a new column called department ID. This column will serve as the foreign key reference that corresponds directly to the department ID in our departments table. By doing this, we're linking employees to their respective departments. It's like connecting the dots. Now, here's the important part. The foreign key constraint ensures that any entry in the department ID column of the employees table must match an existing department ID in the departments table. This is crucial because it enforces relational integrity. With this solid structure in place, we can perform more complex queries. Imagine the insights we can gain by merging data from both tables, such as discovering which employees belong to which departments. Isn't that fascinating? Now that we have our foundational tables established, let's see how we can insert data into these tables. We begin with the Insert Into statement for the Departments table, which allows us to add multiple department names in one go. By specifying the column Department Name, we ensure that each department we list, Human Resources, Engineering, and Marketing, is accurately captured in our database. This structured approach not only populates our departments table, but also sets the stage for linking employees to these departments. Next, we move on to inserting records into the Employees table. Here, we specify the columns for Name, Department ID, and Salary. Each employee is associated with a particular department through the Department ID field, which links back to the corresponding department in the Departments table. This relational aspect is crucial as it allows us to maintain organization and keep track of which employees belong to which departments. With this insertion, we effectively create a foundation for the ongoing data management tasks that will follow. Next, we will write the following SQL statement to retrieve valuable information from our relational database. This code utilizes the join operation, which is essential for combining data from different tables based on shared attributes, specifically the department ID. By selecting employees.name, departments.departmentName, and employee salary, we are creating a comprehensive view of our workforce, linking each employee to their respective department. The From clause specifies that we are pulling data from the Employees table, while the Join clause seamlessly merges the Departments table. The On condition establishes the relationship between the two tables, ensuring that we only return rows where the Department ID matches between the linked tables. This method allows us to generate insightful results, facilitating data analysis and reporting. Now the output of this query will yield a list that not only names the employees, but also presents their corresponding departments and salaries, giving us a clearer understanding of the organizational structure. The displayed figure is a bar chart titled Employee Distribution Across Departments, and it shows the number of employees across 5 key departments. Human Resources has 15 employees, Engineering leads with 30, Marketing hosts 20, Sales contributes 25, and IT rounds out the group with 10. Each bar is clearly labeled with its exact value, and when you add them all up, you find a total of 100 employees. Now, interpreting this chart, it becomes clear that engineering is the largest department, representing 30% of the workforce. Meanwhile, if we look at sales and marketing together, they account for a significant 45%, with sales at 25% and marketing at 20%. Human Resources takes up 15% and, unfortunately, is the smallest department at just 10%. So, what do these numbers tell us? Well, we can see a strong concentration of staff in engineering and a notable combined presence in the customer and product-facing functions like sales and marketing. Conversely, the IT and HR departments show relatively low staffing levels. From these counts, one can conclude that this organization's workforce is skewed toward engineering roles and those that drive revenue generation, while support functions have a smaller footprint. These proportions are not just interesting to note, they're directly visible and can actually guide resource allocation decisions, help with capacity planning, and even inform targeted queries or aggregations when analyzing headcount across departments. Now, let's see how we can enforce essential data integrity rules in our employees table using constraints. The first part of the statement alters the structure of the table, specifically adjusting the name and salary columns to ensure that neither can hold a null value. By applying the not null constraint, we make sure that every employee record requires a valid name and salary, which are critical attributes for maintaining accurate employee information. Additionally, we introduce a unique constraint on the name column, This prevents duplicate entries of employee names within our table, ensuring that each employee can be uniquely identified by their name. Aha, which really enhances the reliability of our dataset. Together, these constraints help uphold the quality of data, preventing inconsistencies and errors that could arise from null values or duplicate names. By implementing these changes, we're creating a more robust framework for our employee data, thereby supporting better query results and overall data integrity across the board. Now, let's dive into how we can implement an index to optimize data retrieval in our employees table. We're going to use a command that creates an index named IDX salary on the salary column of the employees table. Now, why are indexes so important? Well, they play a crucial role in enhancing the performance of frequently executed queries, especially when we're dealing with large data sets. By placing an index on the salary column, we enable the database to locate employees based on their salary much more quickly than if it had to scan the entire table for each query. However, it's also important to consider that while indexes significantly speed up read operations and improve query response times, they do come with additional storage requirements and maintenance overhead. So we really want to be strategic about which columns we choose to index based on usage patterns. In this case, indexing the salary column makes a lot of sense, particularly if salary-based queries are common. This way, we can ensure maximum efficiency in how our database responds to such requests. Now, let's dive into computing some really important analytical metrics using SQL aggregate functions. So, in the query we're looking at today, our goal is to find out the average salary of employees for each department. And why is this important? Well, it helps us understand how salaries are distributed across the entire organization. We're going to start by selecting the department name from the Departments table. Then we'll apply the AVG function to the salary column from the Employees table. The AVG function calculates the mean salary for our dataset, giving us a clearer picture of compensation within the different departments. To make this analysis even more insightful, we'll join the Employees table with the Departments table on the Department ID. This is where we establish a connection based on the foreign key, ensuring we accurately pair employees with their respective departments. Finally, we'll group the results using the Group By clause applied to the department name. This means that the average salary will be calculated for each unique department, resulting in a comprehensive summary of how each department compensates its employees. This aggregation technique can really uncover valuable insights for HR and management, enabling them to make well-informed decisions regarding salaries and budgeting. Now, let's see how we can update an employee's salary using SQL. The update statement is a powerful command that allows us to modify existing records in our database. In our example, we are updating the salary of an employee named John Doe to $70,000. This operation is essential in maintaining accurate and relevant data, especially when circumstances such as pay raises occur. The set clause specifies the new value for the salary attribute, while the where clause ensures that only the record corresponding to John Doe is affected. This precision is crucial in a database as it prevents unintended changes to other records. Next, we'll write a command to remove an employee's record from the database. Using the delete statement, we can proactively manage our dataset by eliminating records that are no longer necessary, such as when an employee leaves the organization. In this case, we are removing the record for Emily Davis from the Employees table. The simplicity of this command highlights SQL's effectiveness in data management, allowing for straightforward updates and deletions to keep our dataset aligned with real-world conditions. Now, let's see how we can enhance our existing employees table by adding some essential contact information. To achieve this, we'll be using the alter table statement, which allows us to modify the structure of an existing table without losing any of the data already stored in it. In this instance, we'll add two new columns, email and phone. The email column will be of type varchar 100, meaning it can store strings of up to 100 characters. That's plenty of space for most email addresses. The phone column, on the other hand, is defined as varchar 15 to hold typical phone numbers, ensuring that we can capture various formats without running into limitations. This command perfectly exemplifies the flexibility of relational databases, allowing us to adapt our data structure as business requirements evolve. By integrating new attributes like contact information, we're enhancing our database's utility and providing a more comprehensive view of each employee. Through this approach, we're ensuring that our database remains a dynamic tool for managing valuable information efficiently and effectively. As we wrap up our exploration of the relational data model, it's become clear that this structure offers a highly efficient framework for organizing, manipulating, and analyzing data. With a solid grasp of how tables, keys, and constraints work together, and the powerful capabilities that come with SQL, you're truly equipped to tap into the potential of relational databases. Now, remember, mastering SQL isn't just about memorizing syntax. It's about learning to think in terms of data structures and relationships. As you keep practicing and applying these concepts, you'll find that the relational data model serves as an invaluable foundation for building data-driven applications and systems. So I encourage you to embrace this knowledge. Keep experimenting, and before long, you'll be navigating the complexities of databases like a seasoned pro. Happy querying!